Okay, in this movie we'd like to talk about Newton's three laws of motion. These are very important laws that Newton came up with, and they're fairly easy. I think most of you have heard of them before. This first law, which sometimes we refer to as the law of inertia, says that an object at rest will stay at rest and an object in motion will stay in motion unless acted upon by a force. So if you have an object at rest or you have an object that is in motion, constant velocity is what we mean by in motion, then all of the forces would be balanced. If you have an unbalanced force, which means you have a force like in one direction greater than the force coming in the other direction, then you're going to end up with a net force in a certain direction. And whenever you have a net force in a certain direction, you will also have an acceleration. So if we have a force this way and a force this way that are equal, then this object will be traveling at a constant velocity. Now that could be a constant velocity of 0, which means that it's rest, or it could be actually a constant velocity of like 50 miles per hour. A lot of times people think, well, if a car is going at 50 miles per hour, there's a force working on it. Well, there would be, but there'd be a force working this way with like the accelerator, the wheels on the road. But there would also be friction force that would be going the opposite way that would be equal to that would maintain a constant velocity. So this was kind of bizarre when Newton said this, because people thought, well, everything tends to come to rest. And Newton said that's only because there is a friction force that works against it. But if you balance out the friction and the force that's propelling the car forward, then you have balanced forces and you still have a constant velocity. So the object that is going to stay at rest or it's going to stay in constant motion will always stay that way unless there's some force that works against it to slow it down or to speed it up. And if there is a force, a net force, then we have Newton's second law, which is called the law, generally it's called the law of acceleration, And this law says that an object's acceleration is directly proportional to the force applied and inversely proportional to its acceleration. And the way we write that is in Newton's second law, very important second law. We write that in an equation form, which is F equals ma, or F equals ma. And this means that if you apply a force to a mass, the mass will accelerate. So this is a net force. It can't be a balanced force. If it's a balanced force, then there will be no acceleration. So this force here we might want to call net force. So if there's a net force applied to a mass, it will accelerate. And you'll see that force and acceleration are directly related, which means if I keep the mass constant and I apply a larger force to a constant mass, it will accelerate at an even higher rate. Or if I if I increase the mass, and but with the same amount of force, I keep the force constant on a greater mass, then acceleration is actually going to be less than what it normally is. So if I keep the force constant and I increase the mass, I make something more and more massive, then that means the acceleration rate is going to go down. Because I have the same amount of force on a larger mass, my acceleration rate will go down. So what are the units for force? Well, if we can derive the units, we know that mass is in kilograms. If we're going to derive this in the MKS system, acceleration is in meters per second squared. So we get this unit of a kgm per s squared, which looks kind of like an ugly unit, but it is correct in the MKS system. But what we do a lot of times is we rearrange, or we rename these MKS units. So this is called 1 Newton. A kgm per s squared is called a Newton. So force, the units for force are given in newtons. And so this is Newton's second law, the law of acceleration, that if you apply a force to a mass, it will accelerate, and we use that for an equation. We can also write it in a different form. We could write it in the form of W equals m times g. This is exactly the same law. A lot of times in physics books you'll find these two equations written in different parts of the book. They're exactly the same law. It's just that when we're dealing with this one, we're usually thinking about something that's kind of vertical. So if I have a box, there is a force downwards, and it's equal to the mass times gravity. So if this is on the Earth, we're going to take mass times the acceleration, which is gravity, or 9.81. We have an acceleration. We know what it is specifically. So we could take the mass of the box times the acceleration of gravity and get its force downwards, or what we call its weight. So these two laws are identical. They're the exact same equation. We just use different variables because we're thinking about it maybe a little bit differently. If we're talking vertically, we're going to use this. If we're talking back and forth like on a road, we're going to probably use this equation here. Okay, so if we kind of put that together, we can look at a problem here. Let's look at this problem here. It says a car weighs 15,000 newtons. What force is required to accelerate the car at 4 meters per second squared? So it says what force is required to accelerate the car at 4 meters per second squared. So clearly I need the force, and I'm going to use Newton's second law. So I know that F equals, and so that's what I'm trying to find, the force. Force equals mass. What is the mass of this car? Well, we don't know the mass of the car. You might think we do, but if you look at this right here, this is not a mass. This is a weight, or a downward force of the car. So I don't know the mass quite yet, so I'm just going to put in m times acceleration. F equals ma. So the force I need the mass of the car times the acceleration of the car, which happens to be 4. So if I can figure out what the mass of the car is in kilograms, I can solve this problem. So what do I have here? I have the weight of the car. Well, I can still use Newton's second law, but I can use it in this form right here. Here's the weight, and I need the mass to plug into here. So how do I take this equation and solve it for mass? Well, mass would equal the weight divided by gravity. And the weight, we know, is 15,000 newtons. And what's gravity on the planet Earth? Well, it's 9.81. We're going to call it 10 just to make the math nice and easy. So I would have a mass of 1,500 kilograms. 1,500 kilograms. So now I can take my 1,500 kilograms times 4 meters per second squared in this equation, F equals ma. 1,500 kilograms of my mass times 4 would give me 6,000 newtons. It would take 6,000 newtons of force to accelerate this car down the road at 4 meters per second squared. So I hope that problem kind of helps you out with this second law. The third law, I'll go ahead and delete all these things. The third law is usually called the law of reaction, or the law of interaction, sometimes it's called. So this law up here was called the law of inertia, and this law here is the law of acceleration. And this third law is the law of interaction. It says for every reaction, whoops, that's not right. For every action, I should say action. Sorry about that. Let's see. I'll just cross off the re. For every action, there is an equal and opposite reaction. And so, what this means is that if I push off of something, like if I push off of the wall, I'd be applying a force to the wall. Then we would also say that the wall is applying the exact same force on me. And so we can't really distinguish on really who's applying the force or not. Let's say we have a car that's going down the road, and here's the windshield, and there's a little mosquito flying around out here, and the mosquito's going this way, and the car's going this way, and they hit each other. And so you'd ask yourself the question, which which object applied more force on the other object? Did the mosquito apply more force on the windshield, or did the windshield apply more force on the mosquito? And most students are tempted to say that the windshield applied more force on the mosquito because the mosquito is not going to win in this situation. But according to Newton's third law, for every action there's an equal and opposite reaction. So with whatever force the mosquito hits the windshield is applying the same amount of force on the mosquito. So the difference is that if I write the equation, I'll write F, and I'll write a certain capital letter, so it's going to equal that amount. This will equal the mass of the acceleration, or the mass of the mosquito, which would be a really tiny mass, times its acceleration. Well, it's going to have a pretty decent acceleration because it's going a certain speed this way, and it's going to be almost instantaneously going the other velocity, the velocity of the car the other way. So this is really, really, really going to decelerate really, really quickly. This mosquito is. But what about the car? Well, I know it's the same amount of force because of Newton's third law. But in this case, the mass of the car is big. The mass of the car is big. So to keep the exact same amount of force, what has to happen to the acceleration of the car? Well, it would be very, 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 very small. In fact, almost basically zero. So it's the same amount of force that the mosquito applies on the car that the car applies on the mosquito, but the difference is that the mosquito has really, really, really small mass, so it has a really, 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 really big deceleration, which will definitely kill the mosquito and basically make it disintegrate. The car would also has a really big mass, so its acceleration would be really, really, really small, so that we can have the exact same force here for both of these. And the acceleration is so small that it's basically zero, which means the mosquito has really no effect on the car. So it's the same amount of force the mosquito is putting on the car is putting on the mosquito. But the problem is this force seems really, really big to the mosquito and really, really small to the car, even though it's the same amount of force. And it does that because the mass of the mosquito is really small and the mass of the car is really, really big. So it doesn't seem like there's much force on the car, and it seems like there's a huge force on the mosquito. This is also going to come into play, which is a little confusing sometimes, if you have to take a person that's standing on the earth, like you're standing on the earth. And there's a force of attraction between you and the earth. A lot of times you think that there's just a force of attraction between the earth and you, that's only pulling you down. But technically you both have mass, so you're both pulling on each other with the exact same amount of force, according to Newton's third law. It's just that the force that the mass of you compared to the mass of the earth is really, really small. So when you use the exact same force between you, that is evident in you accelerating. The earth would accelerate towards you. Technically, you can make an argument, but the acceleration would be so small that it would virtually be zero. How come it's so small? Because the mass of the earth is so big. So, and this will come into play later when we talk about Newton's universal law of gravitation. So those are the three laws of Newton's motion. Hopefully they make sense. The most important one, the one we use the most in physics, of course, is Newton's second law, because that actually has a physics equation that we use a lot. This is net force equals mass times acceleration. So hopefully that'll make sense, and hopefully you know Newton's three laws.